Welcome, fellow cosmic voyagers. Today we journey into a realm unlike anything you know. It's a place where the familiar rules of our everyday world simply break down. We're talking about the quantum realm. This isn't science fiction. This is the fundamental reality of our universe, operating at the smallest scales imaginable. Understanding this realm is not just an academic exercise, it's the key to unlocking the deepest secrets of existence itself, from the hearts of stars to the technology in your pocket. So, buckle up. The universe is about to get wonderfully weird and profoundly interesting. Quantum mechanics is the science of the very small. Think atoms and the tiny particles within them, electrons, protons, quarks. Down there, things behave in ways that can seem utterly baffling. Particles can be in multiple places at once. They can tunnel through barriers that should be impenetrable. They can even be linked across vast distances, their fates intertwined. It's a world that challenges our intuition, built from experiences in our macroscopic world. But it's a world that, once we begin to grasp its principles, reveals an astonishing and elegant order. The journey into the quantum realm is a journey into the heart of reality itself. Let's begin this extraordinary exploration of the universe's most fundamental operating system. So, what exactly quantum mechanics? In simple terms, it's the set of rules that govern the behavior of matter and energy at the atomic and subatomic levels. Think of it as the instruction manual for the universe's smallest building blocks. Classical physics, the physics of Isaac Newton, does a fantastic job explaining how apples fall from trees or planets orbit stars. But when you zoom way down to the scale of atoms, those classical rules just don't cut it anymore. A new set of rules was needed. These new rules emerged in the early 20th century. Scientists discovered that energy isn't continuous, like a smooth ramp. Instead, it comes in tiny, discrete packets called quanta. Imagine energy as currency. You can't have half a cent, you have individual cents. This idea of quantization was revolutionary. It meant that energy could only be absorbed or emitted in these specific amounts. Quantum mechanics tells us that particles like electrons don't just behave like tiny billiard balls, they also behave like waves. This is called wave-particle duality. An electron can be a localized particle in one instant and a spread-out wave in another. This dual nature is not an either-or situation but a both and reality, depending on how we choose to observe it. Let's dive into one of the most famous quantum peculiarities, superposition. Imagine a coin spinning in the air. While it's spinning before it lands, is it heads or tails? In a way, it's both and neither until it settles. Superposition is something like that, but for quantum particles. A particle, like an electron, can exist in multiple states at the same time. It could be in multiple locations at once, or have multiple energy levels simultaneously. It's not just that we don't its state is genuinely a combination of possibilities. Think of a light switch that isn't just on or off, but can be in a state of on and off at the same time. That's superposition. An electron, for instance, might not have a definite spin direction, up or down, until we measure it. Before measurement, it exists in a superposition of both spin-up and spin-down states. The act of measurement forces the particle to choose one state. This concept might sound absurd from our everyday experience. But in the quantum world, this both-at-once reality is standard operating procedure. Superposition isn't just a theoretical curiosity, it's a key ingredient in emerging technologies like quantum computing. Now let's explore another quantum phenomenon that Albert Einstein famously called spooky action at a distance. This is entanglement. Imagine you have two quantum particles that are linked together in a special way. They are entangled. Once entangled, these particles remain connected, no matter how far apart they are separated. They could be in the same lab or on opposite sides of the galaxy. Their fates are intertwined. What happens to one instantaneously affects the other. Let's say these two entangled particles have a property like spin. If you measure the spin of one particle and find it spin up, you instantly know that its entangled partner, wherever it is, will be spin down, or vice versa, depending on how they were entangled. It's as if they are communicating faster than light, but they aren't sending signals in the classical sense. It's a deeper, more mysterious connection. The correlation is perfect and immediate, regardless of the distance separating them. Entanglement is not just a puzzle for physicists, it's also a resource. It's crucial for technologies like quantum cryptography and quantum teleportation. Section 5. The universe's grand experiment, the double-slit. Perhaps no experiment better captures the strangeness of the quantum world than the double-slit experiment. It's simple in setup yet profound in its implications. Imagine firing tiny particles like electrons one by one towards a barrier with two narrow slits in it. Behind the barrier is a detector screen that records where each electron lands. What pattern would you expect to see on the screen? If electrons were just tiny billiard balls, you'd expect two bright bands corresponding to the two slits. But that's not what happens. When we perform this experiment with electrons, we get something astonishing. We see an interference pattern on the screen, a series of bright and dark bands. This is the kind of pattern you get when waves like water waves or light waves pass through two slits and interfere with each other. The peaks of the waves reinforce each other, creating bright bands while peaks and troughs cancel out, creating dark bands. This tells us that electrons, which we thought of as particles, are behaving like waves. Now here's where it gets even weirder. What if we try to find out which slit each electron goes through? We can place a detector near the slits to observe the electrons' paths. If we do that, the interference pattern vanishes. Instead, we get the two simple bands we'd expect from particles. Section 6. Architects of the Quantum Realm, Niels Bohr. No discussion of quantum mechanics would be complete without mentioning Niels Bohr. This Danish physicist was a towering figure in the quantum revolution. Born in Copenhagen in 1885, Bohr made foundational contributions to understanding atomic structure and quantum theory, for which he received the Nobel Prize in Physics in 1922. Bohr's most famous contribution is perhaps his model of the atom, proposed in 1913. He suggested that electrons orbit the nucleus in specific energy levels or shells. They could jump between these levels by absorbing or emitting quanta of energy, but they couldn't exist in between. Bohr's model, though later refined, was a crucial step in understanding atomic stability and spectra. Bohr also championed the concept of complementarity, suggesting that phenomena can have seemingly contradictory properties like wave-particle duality, but that these properties are complementary aspects of a single reality. Section 7. The reluctant revolutionary, Albert Einstein's quantum doubts, Albert Einstein. The name is synonymous with genius. While he's most famous for his theories of relativity, Einstein also played a crucial role in the early development of quantum theory. In fact, he won his Nobel Prize in Physics in 1921, not for relativity, but for his explanation of the photoelectric effect. Despite these early contributions, Einstein became one of quantum mechanics' most famous critics. He was deeply troubled by its probabilistic nature and its apparent randomness. He famously declared, "God does not play dice with the universe." He believed that quantum mechanics, as it was being formulated by Bohr and others, was an incomplete theory. He felt there must be underlying hidden variables that, if known, would restore determinism and certainty to the subatomic world. Section 8. The Cat in the Box. Erwin Schrödinger and wave mechanics. Another giant in the quantum saga is Erwin Schrödinger. This Austrian physicist, born in Vienna in 1887, made monumental contributions to the field, particularly with his development of wave mechanics. In 1926, Schrödinger formulated a groundbreaking equation, now known as the Schrödinger equation. This equation describes how the quantum state of a physical system, represented by a wave function, changes over time. Schrödinger's wave mechanics provided an alternative yet equivalent mathematical framework to Werner Heisenberg's matrix mechanics. His approach, focusing on waves, was often more intuitive for physicists to work with. The wave function, denoted by the Greek letter psi, psi, contains all the information about a quantum system. The square of its magnitude gives the probability of finding a particle in a particular state or location. To highlight what he saw as the absurdity of applying quantum superposition to macroscopic objects, Schrödinger devised his famous thought experiment, Schrödinger's cat. Section 9. Quantum leaps, shaping our modern world and beyond. The journey into the quantum realm, from its perplexing paradoxes to its elegant equations, has been nothing short of revolutionary. The discoveries made by Bohr, Einstein, Schrödinger, Heisenberg, Planck, and many others haven't just rewritten physics textbooks. They have fundamentally reshaped our world and our place within the cosmos. Quantum mechanics is not just an abstract theory, it's the invisible engine powering much of our modern technological society. Its impact is profound and pervasive. Consider the device you might be using to read this, or the screen you're watching it on. Transistors, the building blocks of all modern electronics, computers, smartphones, televisions, operate based on quantum mechanical principles. Lasers, used in everything from DVD players and medical surgery to industrial cutting and telecommunications, are a direct product of understanding how electrons jump between energy levels in atoms. Without quantum mechanics, the digital revolution simply wouldn't have happened. Our daily lives are steeped in its applications, and the quantum revolution is far from over. Scientists are learning to manipulate individual quantum systems with unprecedented precision, leading to transformative technologies like quantum computers and quantum communication.